plus. Okay. A plus. Okay, so let me talk about the midterm. I know you guys can't see the screen right now. But so the midterm, it's mostly mathematical in nature. I would say review homework 1, okay? Kind of, oh, what do I tell you? All right. Okay, I'll go ahead and tell you stuff then. One of them will be you're going to minimize a loss function, right? There's gonna be a loss function. You have to minimize it. Find the parameters that minimize it, okay? And you'll be expected to work that out. Another one, you'll be given another function, and you're gonna have to figure out the likelihood and maximize the likelihood, okay? And find the maximum likelihood estimates. So I feel like that you guys should be able to do that, right? We know how to do this, right? You figure out the function, and then you set the derivatives equal to 0, solve. Easy. Yes. Well, I'm giving you.
It's not like a Y.
It's not crazy. It's not crazy, okay? And then one more. You'll have there's going to be minimal graphing and calculating. So if you have a straight edge or a credit card or something, something that you can use to write a straight line, then you can do that. So one, I'm going to give you. I'll say. I'm giving it too. I'm telling you too much. Huh? Okay. Huh? Yeah. So okay. So is that good? All right. There's I'll give you. What can I say without giving away the exact problem here? So we've learned some. You learned some stuff in this class, and you're expected to. There's an algorithm you learned, and you're gonna have to do the algorithm manually. It's as straightforward as I can make it. I'm expecting everybody to do well. I mean, of course, I get it. Some of us have bad days, and sometimes just on the test, your brain stops and then you're stuck. But I feel like it's very straightforward. If you come back and you give me feedback that it was a terrible exam, then I'll have to reevaluate my life. But we'll be okay. All right. Question?
What was the second one you said? You're giving us a function.
You got a probability density function, right? And then to describe how data might be generated, and given a set of data, you want to find the maximum likelihood estimate. So it's
How many questions?
It's 3 questions. Okay.
Is one of them, are you here, true, false?
Maybe I'll throw that in there, okay? I'm here, true, false. Yeah. Okay. Yeah.
Which chapters in the book is...
Chapters 1 and 2 from the textbook. Okay. Chapters 1 and 2 from the textbook plus notes, right? Because I covered some stuff in the notes that wasn't in the textbook. So review your notes as well. Okay.
Sorry, the first one was just minimizing the loss function.
Minimize the loss function. Yes. What's going on? Are these still not turning on? Okay. Maybe they're all right. Yeah. Minimize the loss function. Find the estimates that minimize the loss function. Find the estimates that maximize the likelihood. Apply one of these algorithms that we learned. Yeah.
Do we get to bring a cheat sheet, or do we not need it?
No cheat sheet. You got to be able to do this, okay? If I give you a cheat sheet, it's gonna be like, you're just gonna be copying from the cheat sheet onto the midterm, okay? So no cheat sheet, okay? Yeah.
When will homework grades be up?
When will the homework grades be up? So I made a big mistake. This was completely my bad. Well, a tiny bit the reader's bad, but I thought I sent the reader the solutions for homework 1, but apparently I hadn't. So the reader was just like, well, I'm waiting for your solutions. And so that's why homework 1 hasn't been graded. So I'm sending them over and I'm saying, please grade these as soon as possible. But that was my mistake. I thought I'd sent the solutions in.
What's the solution for the
Maybe. All right, I'll think about this. I don't know. Yeah, I know. Yeah. I'll think about whether I post the solutions for the homework or not. Okay. So okay. Anyway, that's that. All right. We'll talk about today's lecture content. 102B, week 5, Wednesday. Okay. Oh, okay, great. So now we're going to start chapter 3 in the textbook, okay? And we're going to look at a little bit of Bayesian learning, okay? Or maybe I shouldn't call it Bayesian learning, but we'll just say Bayesian statistics. And I guess before I get into it, who here is familiar with Bayesian stats? Okay, like 4 of you. Or and then so wait, so has never dealt with Bayesian stats before? Raise your hand, kind of. All right. Okay. Okay. So we have like 15% participation in my poll. Okay. Well, we'll take a look at this because this kind of sets a little bit of the framework that we use for some of these things that we're doing. Okay. Now, I have to be selective about these. I have to be selective about what we cover because I absolutely must cover principal component analysis, which is chapter 7 in the textbook. That's like one of the key things that we have to cover in this course, and if I don't do that, then I'll get in trouble. So I have to make sure I get to chapter 7, which means between now and week 10, I'm going to have to selectively choose some of the content that we cover. So if you're really hoping to go through every chapter in the textbook, I apologize. We're going to have to skip some sections. But today we're going to just start with kind of this Bayesian thinking here, and we still offer the course on Bayesian stats, right? Is that what, 180 something, 170? I don't know, something.
Rare.
Huh?
Very rarely.
Oh, it's very rare? Oh, you guys are missing out.
I guess you have to teach it.
Yeah, well, we'll see what happens. I'm still planning out my 102C class. Oh, okay. So I wanted to talk about 102C. I know on the registrar it says the final is like that Friday of that week, and that's like graduation, and so don't let that be a deterrent, okay? We'll figure something out, all right? We'll make sure this final thing works out with graduation. I don't want you guys to miss graduation. So what? Just don't have a final? Yeah, I'll get in trouble for that. But so I have to have a final, but we'll make sure it works out between the scheduling and the graduation and all of that. But also there's other teachers teaching 102C. and they're all very good, okay? I feel like I'm the least qualified one to teach 102C, but, but we'll have fun in the class, so. All right. Well, I hope you guys are having fun in this class. I'm having fun. Maybe it's different. Okay, so let's talk about Bayesian stats. Okay, so we're going to start off with the example, and I'm going to use the example straight from the book, so if my explanation doesn't make sense, you can always go to the textbook, and I hope maybe it'll make sense that way, okay? So we're imagining ourselves at a carnival, okay, and then there's a carnival game. And the carnival game seems too good to be true, which, if you haven't learned in life yet, if it's too good to be true, it probably is. And the way the carnival game works is that, the person running the game says, I'm going to flip a coin 10 times. And if it lands heads 6 times or less, you win. And you go, wow, that seems pretty good. Okay, if it lands 6 times or less, you win. And if it lands heads 7 times or more, you lose. Okay? So, we can calculate the probability of winning and losing using what kind of model here? Flip a coin 10 times and we want, this is binomial, right? We should know this, okay? So this is a binomial model, and if we assume a fair coin, then the probability of heads is 0.5, okay? And for whatever reason, the textbook chooses to use R for the probability of heads. I don't know why, but that's what they did. And so therefore, for the binomial model, do you guys remember what binomial looks like? And we have n choose, it's going to be y, okay? N choose y, and then it's not p to the y, but now it's going to be r to the y times 1 minus r to the n minus y, yeah. Okay, and so in this case, our n is equal to 10, our r is 0.5, okay? And then we can find, what's the probability that y is going to be less than or equal to 6. Okay, and so this would be basically the sum, or I'll just write probability that y equals 0 plus probability that y equals 1 plus through probability that y equals 6, right? And what if I wanted to do this in R, how can I do this? Yeah, so we can do, there's a few ways. We can do p binom. You guys familiar with these R functions? Maybe? Okay, so I do p binom 6, 10, 0.5, right? Or another way is I could do sum d binom 6, I'm sorry, not 6, 0 through 6, 10, 0.5, yeah? Okay, so let's go ahead and try that over here. So I can do p binom 6, 10, 0.5. What? I don't know what just happened. Why did he give me an error here? Do catch. Oh, I must have touched something else. Okay, well it says 0.828, okay? And then the other way is I could say d binom 0 through 6, and I could say sum this up. Okay, and that gives me the same thing. So sum of d binom and p binom 6, 10, 0.5. it seems like, oh, we're gonna have a 83% chance of winning, right? If okay, so if our assumptions are correct, we have probability 0.828 of winning. Okay. All right. So far, so good, right? Okay, and then based on that, we can also say, well, our winnings. If we want to model our winnings x, we could say, and the probability of x. Okay. So if you bet $1 and you win, you'll get back $2, and then if you bet $1 and you lose, you get back 0. So the outcomes are going to be 2 and 0, and we if everything's correct, then our probability of winnings would be 0.828, and then the probability of losing would be, what is this, 0.172, okay? And then therefore my expected x would be 2 times 0.828 plus 0 times 0.172, and I get whatever this is times 2, 1.656, okay? So that seems like a good deal, okay? But of course, you look at, you're like, well, this doesn't make any sense, right? And if it doesn't make sense, then trust your gut. Don't play the game. You observe, okay? Watching the you watch people play, and most of the time people lose. So what's going on? Okay. Well, we had 2 key assumptions. Okay. One is the binomial model. And then maybe, as far as the game goes, you're flipping a coin, so there's only 2 outcomes. And as you're watching, it seems like the coin flips are independent, right? I mean, it's hard to really check this without interfering too much, but this assumption is probably not violated, okay? This assumption is probably not violated. But the other assumption is that the probability that it lands heads, being 0.5, perhaps this is not quite right. Okay, so let's say you observe someone play, okay? You watch one person play. And this person gets 9 heads out of 10 flips. Okay. So based on this data, what is our maximum likelihood estimate of R? All right, so let's, I guess on the next slide we'll work out how to calculate the maximum likelihood estimate of R. Okay, so what we have is, our PDF, I mean not our PDF, yeah, our probability density function, actually it's a mass function. No, well, okay. The probability of y equal to y given some values r and n, we said is n choose y, r to the y times 1 minus r to the n minus y, okay? Now if we just have one one observation, one game, then we don't have to worry about multiplying a sequence of all of these together. Okay, so we just have one. This is our likelihood. Okay, given our data. Okay, so we want to find the R. Find the R that maximizes this. Okay, so just. Okay, so what can we do? So we're going to do the R that maximizes this will be the same R that maximizes the log of this. Okay. Okay, and so the log of this I get log of n choose y plus y log r plus n minus y times log of 1 minus r. Okay, so this is my likelihood, log likelihood. And we want to maximize this, so we're going to take the derivative with respect to r, and we're going to set this derivative equal to 0. Okay, so the derivative of this with respect to r is 0. What's the derivative of y log r? Y over r. Okay, and the derivative of n minus y times log 1 minus r? Okay, n minus y times divided by 1 minus r, and then chain rule, we multiply this by a negative 1, right? Okay, and then we just set this thing equal to 0. So over here I get y over r is equal to n minus y over 1 minus r. I have y times 1 minus r is equal to r times n minus y. Got y minus yr equals r. I'll do nr minus yr. The yr's cancel. We got y is equal to n times r, and therefore the r that maximizes this, or the r where our derivative is equal to 0, is y over big N. Okay. So if my data has n equal to 10 and y equal to 9, then my r that maximizes this is going to be 9 over 10 or 0.9. So here we found the maximum likelihood estimate based on our data here. We're finding the value of r that maximizes the data that we saw. Okay, and I mean, and this I think makes intuitive sense that the proportion that we're estimating is that if it landed heads 9 times out of 10, we would say that the best guess would be that the coin lands heads 90% of the time. Okay, so we have this, and when we if we take this value of r, we can go back and say, well, what's the probability of winning if r is equal to 0.9? Okay, so then what is the probability of winning? R is equal to 0.9. Okay, well now we have. Now we can say, well, probability that y is less than or equal to 6, this would be p binomial, 6 given 10.9. Okay, and when we calculate this out, it's a really small number. So if I do p binomial 610.9, it says it's only 0.012795, so 0.0128, okay? Okay, so that's pretty small. It's about 1% of players, a little over 1% of players win, okay? Okay. However, you know, this answer itself doesn't quite align with your observations of the game. Okay, so it seems like more than 1% of players are winning. Okay, but we'll say, you know, but this rate of, you know, 1.28% does not seem to align with our observations, okay? It does seem like more than this percentage is winning, okay? Okay, and so what we're going to do is we're going to say, well, okay, well, I can look at more data. I can try to gather more data and see. But what we're actually going to do, the Bayesian way of thinking is not that we're going to try to settle on a specific value of R, okay? So maximum likelihood estimation, you're saying, I want the value of R that maximizes my likelihood, okay? With Bayesian statistics, or Bayesian reasoning, we're going to treat R itself, the probability that the coin lands heads, we're going to treat that parameter as a random variable itself, okay? So we will treat R, so this as being as a random variable. Okay, so this R, this is the random variable of the probability of landing heads, okay, for the coin. And we're going to say, you know, kind of our estimate of R itself depends on the data we see, okay? So R here, lowercase, our estimate of R, you know, depends on the data we observe. Okay. So with Bayesian thinking, the key here is, again, you know, the parameter is treated as a random variables, okay? And what we're hoping to get is not a single value estimate of our parameter, but rather a distribution of that variable. We want to say these values, based on our data, these values are most likely for the parameter, these values are less likely, okay? So the parameters are treated as random variables. We are not trying to find, you know, a single value estimate of the parameter. Okay. Instead, we aim to get a distribution of the resulting distribution of the parameter. Okay? And thus we can say, you know, so our conclusion will be along the lines of, based on our data, based on our data, these values of R are likely, and these values of R are unlikely. So this is a significant shift in the way we're thinking about parameter estimates, okay? Because before, this kind of talk was nonsense, all right? Right? Because if we had the frequentist view of probability, it would be the parameter, the probability that the coin lands heads. That's a fixed value. It's 0.5, or maybe it's a biased coin and it's 0.7. It's something like that, okay? It's a property, it's a fixed property of the coin, okay? That's the frequentist view. There's no uncertainty about the probability that the coin lands heads. It's a fixed value at something, okay? What we're saying here is, you know what? We don't really know the property values of this coin, and it's kind of unknowable. We don't know exactly the probability that the coin lands heads, and so all we can do is we can just study, look at the data that this coin produces, and based on the data, get an idea of its parameters. We can say, well, after flipping the coin a bunch of times, it seems like 0.5 is a very likely estimate, okay, but so is 0.48, anything between 0.48 and 0.52. Those all seem like pretty likely estimates for what this thing is, because you know what, we don't actually understand physics, and we don't actually understand all of the inner workings of what happens when you flip a coin. We're just saying, when we look at this, this is what we're thinking. I'm pretty confident that the probability it lands heads is not going to be 0.9. But looking at this coin flip, I can't know for sure what that property is. Okay, that's a significant paradigm shift in terms of probability between the Bayesian thinking and frequentist thinking.
Could you give another application of this besides a coin flip?
Yeah. So, when we're talking about just any kind of probability, okay, so. A lot, I think kind of our natural tendency for probabilities is Bayesian in viewpoint, okay? Because if you think of what's the frequentist definition of probability? It is the long run relative frequency, right? Like if we could repeat this thing over and over and over again, it is, the relative frequency of this outcome, right? But, you check the weather, right? And it says there's a 40% chance of rain tomorrow, okay? What does that mean? Or, it says there's a 50% chance of rain tomorrow, whatever it says. The Bayesian thing is, well, at this point, we can't predict the future. All we can say is, the likelihood of it raining is just about as likely as it is not raining, okay? And that's kind of our natural interpretation when it comes to Bayes, right? And if it says there's a 90% chance of rain tomorrow, we're saying, well, given tomorrow, we're thinking 90% chance it's going to rain. Whereas if we were frequentists, if we hear this number, 90% probability of rain tomorrow, it's kind of this, it's a silly idea, but it would be like, okay, well, we're going to freeze time now, and we're going to have like a million parallel universes, and then we're going to just play out what happens, and in 90% of these parallel universes, it rains, and in 10% of them, it doesn't. It's kind of like that idea. Obviously, that we can't physically test that, but the frequentist view was developed from kind of these games of chance, where it made sense to repeat something over and over and over again. That kind of thinking made sense. But with Bayesian things, we're kind of saying, we can't know this thing for sure. We can't say it's going to be this one value. We're just trying to get the the distribution of R given our data. Okay? Does that kind of make sense? So we are going, so we want the probability distribution of the parameter R based on our data Y. Okay, and so we can write this. We want the probability of R given Y. Okay, so for the binomial, we will say capital Y little sub n. This is going to be our random variable, and this is the number of heads we observe after n coin flips. Okay, so this is what we're going for, and so this, you know, realizations of this random variable is going to be little yn. Okay, and so what we want what is the probability of R given the data that we observed, right? So what is the probability of R given some observed data yn? Okay, and so now R itself, R is a random variable, y sub n, that's also a random variable. And based on this, now that we have this, we can use this to try to answer the question, you know, what's the probability of winning, okay? Once we have this, okay, once we figure out this distribution, we can find out the overall probability of winning. Okay? So the overall probability of winning is the probability that some new observation is going to be less than or equal to 6, right? So I can just write y sub new. This is going to be the overall probability of winning. Okay? Now keep in mind that this probability that y is less than or equal to 6, this is effectively, we have to think of, you know, kind of, we've got the binomial of basically, can I just write p binom instead of writing out the thing? Will it make sense to you that I'm talking about the cumulative binomial probability here? Okay, so I'm going to say this thing is going to be p binom 6 based on n is equal to 10 and some value of r, okay? However, r is no longer a single value. R is now a distribution of values, right? We have an entire range of values that we're going to use for r. So what do we do to try to get this into a single number? Okay. Well, here we would basically do the integral of this for every value of r multiplied by the probability of R given our data. Okay, and then we integrate that over R. And this will give our overall probability here. Yeah. Oh, I'm sorry. This should be a big N here. This is the probability of R given our data. Okay, and here, because, right, we are now getting the distribution of what R looks like, and we're going to calculate, what we're basically doing is we're calculating the probability, the binomial probability for that particular value of R, and every single possible value of R, where some of these values are more likely than others. Okay, and so, you know, basically I can say, you know, what's the probability of getting 6 heads if R is equal to this, okay? And it's gonna, that answer is gonna change from one value of R to another, okay? And to properly weight this and say, well, these values of R are more likely than these values of R, we multiply them by that probability of R, okay? And then we integrate everything. Does this kind of make sense? It's very strange the first time you see it. I'll admit that, okay? So, so anyway, so, you know, so if we want, you know, probability that some new value of y is going to be less than 6, given some observation, this is our observed data, given our data, and this is probability of winning in the future. This is going to be equal to the integral of the probability of winning in the future given, this is the parameter R, and we have to compute this over all possible values of R. Parameter R, and then this is a, you know, a range of values, right? So that distribution of R given our data is this. This is kind of the distribution of R given our data. dr, okay? I know it's an integral. You can kind of think of it, if it's a little bit easier to think of it as a computationally, where you say like, okay, I can figure out, you know, what's the probability of, you know, getting 6 if my R is equal to 0.4, okay? And we multiply it by the probability of getting R being 0.4. And then we say, okay, well, what about with R being, you know, 0.41 and 0.42? And you calculate over the entire range of possible values of R, but you want to weight those different calculations based on the probability of R itself. Oh gosh, I'm talking too much. Okay, so this is the interesting part. Okay, so we want to get. We are now interested in probability of R given our data. R given our data. Okay. So if you recall Bayes' rule, how do we do Bayes' rule, right? So Bayes' rule, do you guys remember Bayes' rule from like your intro probability? What's probability of, we'll say, A given B? Probability A given B is the probability of B given A times the probability of A, right? Divided by the probability of B. Does this kind of look familiar? 100A, 100B? We should have... Yeah, okay, good. Okay, so we're gonna use this here, right? We're gonna say, okay, well, if I want to know the distribution of R given my data, well, we're gonna find the probability of our data given some value of R times the probability of R divided by the probability of our data. So all we're doing is we're using Bayes' rule here. Okay, so let's look at, so we label each of these terms. These all get different terms. This is called, this first one, this is called the likelihood. This is called the prior. And this one's called the marginal. Okay, you got three terms, three probabilities that you're multiplying together. They all have different names: the likelihood, the prior, and the marginal. So we'll talk about the likelihood first, and then we'll talk about the other ones. I guess. Oh, Friday you have the midterm, so it'll be Monday. Oh man. Okay. All right. So let's talk about the likelihood. The likelihood is the probability of yn given r. Okay. Now this is going to look like, it looks like, you know, just like the binomial probability. Okay. But there's a key distinction here. Okay. So it looks just like whatever probability function you're using. Okay. Looks just like, you know, your probability function. Okay, but it's not, okay? It is, but it's not, okay? It is the likelihood of your data, okay? And the key difference here, so this tells us the likelihood of our data. Given a parameter value r. Okay, and the key difference is that if you have a probability function, what's the total area under the probability function? 1, right? That's like the rule for probability functions, that the total area underneath it is 1. Likelihood functions are not the case, okay? When you look at a likelihood function, kind of the variable that you're looking at it over is r, and it's not going to have a total area equal to 1, okay? So the total area of a likelihood does not equal 1, okay? So let me just demonstrate what this looks like. Okay. So you guys are familiar with like d binom. So if I did d binom, this is you know, kind of for the range from 0 to 10. If with 10 flips and the coin flip is 0.5, you know, it gives me the sequence, and I can do a bar chart of all of this. Or I'm sorry, it's bar plot. Okay, so this is you know, our binomial distribution. This is kind of what we're used to seeing. Yeah. Okay. So here's the key difference. This is where with d binom, the thing that was changing was my value x, or the value y, the number of times it lands heads. Okay. This time I'm going to create a range of r. This is r being the probability that it lands heads. Okay. And so here I'm still using d binom, but this time my data is fixed. My data is fixed to be it landed heads 6 times out of 10 flips, and the thing that is changing is the value r. Okay, I'm changing, well, maybe the probability of it landing heads is 0 or all the way up to 1, okay? And so when I plot this, this is what it looks like, okay? This is the likelihood of our data given when r is equal to this. So it makes sense that when it lands heads 6 times out of 10, it's most likely when r is 0.6. Now compare this. Here, this says my coin landed heads 70 times out of 100 flips. Okay, and I'm going to calculate our binomial probabilities, our likelihood of our data, given this different range of r. I'm going to plot this, okay, and the likelihood here is this little blue function, okay, and we can see that the total area under this curve and this curve is not the same, right? These are not probability functions, they are likelihood functions, because the thing that we're changing is not the outcome y, but the parameter r. Okay? And what this says is that when you flip the coin 100 times, then the range of plausible values is much smaller. Only values between here and here are really plausible. This is still the greatest likelihood. The greatest likelihood of getting your data is going to happen at 0.7, but now we have a tiny thing. Okay? We would say this curve provides more information than the other curve because the wider curve, pretty much any of these values are kind of plausible, whereas over here, only values in this range are plausible. Okay, so this is kind of the idea behind likelihood. We'll further explore this with priors and all of this. This will come next week. I'm gonna have to start picking and choosing some of our topics. Good luck as you guys study for the midterm. We'll see you guys on Friday.